So I think we're going to get started. So hi everyone and welcome to another one in our series with the Maryland Robotics Center seminar series. So today we have Chuchu Fan, who is an assistant professor of the Department of Aeronautics and Astronautics at MIT. And so she earned her bachelor's degree from Tsinghua University, and she got her PhD in electrical engineering and electrical and computer engineering at the University of Illinois Urbana-Champaign. And then she was a postdoctoral researcher at Caltech before she ended up at MIT. And so she is a recipient of the NSF Career Award, the AFOSR Young Investigator Program, and we are very excited to have her today. So let's give her a round of applause.
All right, thanks for the introduction, Ryan, and glad to be here. Last time I gave a talk at Maryland was 4 years ago, when I was looking for a job. I ended up getting a job here. I also got a job at MIT. It was a tough choice. But I'm happy to be here 4 years later to talk about what we have done since I joined MIT. And my lab is, as you can see, the name is called Realm. It's like spent some time trying to figure out a name that people can remember. I hope you could remember. It's for Reliable Autonomous System Lab at MIT. And from the name, you can probably tell what we are working on. So we work on developing technologies for the design, analysis, and verification of safe autonomous systems. So at the first page, I want to just give a very quick broad overview of what we are working on. Because of time limit, I will be able to only cover one part today. But happy to talk about the other parts if you are have any interest in any of the other part of the research. So looking at the left, I'm just putting a very, very rough diagram of what computation means in an autonomous system. Autonomous system means something that operates by itself. It doesn't really need a lot of human input for every step. So in a computational pipeline of autonomous system, we all know that we have the sensing perception module kind of acting as the ears, eyes of the robots to know the environment, and they will process the outside environment as some sort of a software representation or a mathematical model for the decision-making and planning module to understand what to do with the current information. And ultimately, this plan has to be executed. So lots of people in robotics, they believe they work on the middle level of decision-making and planning. To me, a lot of the applications I care about, because I'm in the aerospace department, having a plan doesn't mean you can execute the plan. So how to execute the plan, how to execute the plan reliably, control the system, especially the super challenging systems, like the large-scale ones I'm putting in here, is something that's also interesting. So we work on a lot of large-scale system control, and all the plots here, you see the simulation environments that we develop at our lab. You can probably tell there is like a big city, and there are tiny white dots. And those are quadrotors. There are thousands of them flying the city with all the disturbances. They are delivering stuff for us. How do we control all this? Even if the quadrotors know where to go to get the packages, they still need to get there. So how to get a lot of them there simultaneously, and we have a trust in those, is the problem that we study. Similarly, we have the ground version. We also look at very complicated airplanes, like fixed-wing airplanes. So I will talk about that today. I also want to briefly mention we also work on the other levels too. We work on, for the decision-making and planning level, we look at super complex tasks. For example, if I'm routing thousands of electric vehicles in Manhattan, where should I place the charging stations? How should I schedule the electric vehicles there? Get in charged, they can get the people and the stuff at their destination on time, and there's no congestion. So this kind of complex requirements, how do we fulfill those? And another type of setting would be multiple robots. Different types of the robots will have to work together in a warehouse or assemble something together. And each will have different degrees of freedom. Maybe some of them have very high degree of freedom. How would we coordinate all the systems, make decisions so they can work together to execute complex tasks? And recently we have some work on how to bring the very trendy large language model into this picture, having large language model to help us in this communication and then talk to multiple robots. I'll be happy to talk about that if you have interest, or send you the references. And the last piece of work that we work on a lot is assurance. So as the name suggests, we work on reliable system. We want to have some sort of assurance. And here I'm not just looking at sensing and perception, but the entire computational pipeline. How should we provide the assurance cases? How would we how would we test the system and fix the bugs? And this can span across different applications, all the way from the things I have talked about, like quadrotors, to manipulation, power grids. We're developing tools and packages for engineers to provide assurance for their system. So today, as I said, I will probably only cover the bottom part, but happy to introduce more if you're interested in those. And now back to the large-scale control problem. I already kind of talked about this picture here. The difficulty problems we're looking at in safe navigation, and I have robotics because the safe navigation problem, depending on how you define robot, some people think robot would be like a small robot car or manipulator. To me, anything that will have some level of intelligence to operate itself is a robot, including big airplanes. Today, like the robot or the autopilot is flying our airplane. So that is also considered as some sort of robot in our definition. Anyway, so the difficult problems we're looking at are particularly in large scale. The large scale is defined as a large fleet of agents, very high-dimensional systems like high-dimensional state space or input space, unknown or imprecise models for the system and the environment we have to handle. And finally, what type of assurance or guarantees we can provide. So those are the problems we think are very interesting and open challenges still in a safe navigation problem. Now I'm going to talk about how we are addressing this problem using this technology called neural certificate. And you're probably already curious about when I said, like in the title, how the certificate, what is a certificate? How is it related to something people relate to, like a certificate for your robot or a certificate for your airplane, commercialized airplane. They kind of have similar idea, but here we are looking at a more control level of a certificate called control certificate functions. Now, this plot I'm having here listing a couple of examples of certificate functions control people usually use in their design of the system. If you took any of the control class, I'm sure you have seen one or more of those, like Lyapunov function is a pseudo energy function that shows your trajectory will converge to a fixed point or equilibrium point. And that equilibrium point is really the state that your system wants to get to, and it's a desired state. If we find a Lyapunov function, we can say something about the system is get stabilized there, and it's robust to disturbances, depending on how large that disturbance is. And recently, a lot of people look at barrier functions. Barrier function is similar to Lyapunov function, but it's kind of it's a generalized version of it. It will create a barrier. A barrier defines safe and unsafe. Within the barrier, it's safe. Outside the barrier, it's unsafe. And what the barrier function is doing is to, first of all, create this barrier and make sure the system always stay within the safe region. And this is largely used in proving that your system is safe. It won't have any mistaken behavior, even if it's got kind of disrupted. And the last one is called contraction metric. This is something a lot of flying robot people care about, because Lyapunov function can look at a fixed point. But for flying robot, you want it to fly around. You want it to have some sort of dynamical behavior, like a quadrotor we are flying. But for flying robots, you want it to get back to the original trajectory, like your higher level planner give you a trajectory, you want to follow it. A wind come that can blow your quadrotor away. How can you bring it back? Contraction metric there is a tool to guarantee the contracting behavior. So it will certify the ability for the robot to track some arbitrary trajectory. And it's similar to the Lyapunov function. And what we are doing here is to look at the problem of how to find these certificate functions in complex robotic systems. And one thing I want to say is not like we find one at a time. You can find arbitrary combination of those if you want to have multiple properties of the system. And it's not like nobody knows how to find those. There is, like, for Lyapunov function, for example, it's a 100-year history of finding Lyapunov functions. I teach the control class at MIT, and I tell students the entire history about finding the controlling especially nonlinear system, is about finding the optimal function. So it's like a important problem. There has been a lot of methodologies. Luckily, for a large body of the system, people already know how to do it. Unluckily, for extremely challenging scenarios, like a lot of agents, like for this super high-dimensional complicated systems, or when systems do not come with a nice mathematical model, it's still considered as a challenging problem. So similarly for the other type of control certificate. So in this talk, I will talk about a few case studies that we believe is challenging for the traditional approaches to tackle the certificate finding problem. But before that, I want to give you like a picture of where neural certificate can help you with in terms of addressing control problems. We have in the past few years, my lab is largely focusing on this problem, and we have a list of publications here. I just listed the name and the last name of the first author from my lab, but you can find all these papers on our website. We have shown in some work that a neural certificate function can help with single agent systems with learning-based control, but now this control is certified to be robust. It can be used online, and it can be used to in an adaptive way to handle failures or different changes in the environment. We have shown that the big attracting property of very attractive property of neural certificate is it can really generalize well to a very large fleet of agents. We have shown that it can handle very high-dimensional state space and input space systems and large dynamic models. By saying high-dimensional input space, I mean the robot directly take sensor input like images, camera input, or LiDAR input. So those are considered as high-dimensional input. We have looked at how to bring RL into the picture to address this problem that some of the dynamical systems we just do not have an accurate model. Can we have reinforcement learning? Sorry, I didn't list the full name. RL is for reinforcement learning. Reinforcement learning to find the policy, but how we can design this process to also have the certificate function for guaranteeing whatever property that we want. And we also look at how certificate function can help us provide insights on other uncontrolled agents and about how they react to other type of autonomous agent. So in today's talk, I won't have all the time to talk about everything. I will mainly talk about these two relatively recent updates on how neural certificate can help with the two problems I talked about at the beginning, a large fleet of agents, and also how this is used in reinforcement learning. So I will have a more concrete example about what it means by a neural certificate, what type of certificate we can establish for a multi-agent system. But before that, I want to establish kind of the very basic setting of our multi-agent system here. So this is a multi-agent system, although there's only 4. You can see the 4 agents, they are traveling to their destinations. Those brain dots are their destinations. Now what they have as sensors, they have some sort of a sensor at the destination telling them where they are relative to the destination. And they also have the LiDAR. You can see there's very light yellow lines there. They have established that those are basically the LiDAR rays that hit the obstacle and got reflected. So those are the LiDAR points that will be reflected, so the robot knows. And you may also see sometimes the agents can have like a line between them. That means they are close enough and they're willing to establish some sort of a communication channel. So that's the setup we have. Now how would we certify that? In this scenario, the red ones are some moving obstacles. And the robots, they are not supposed to know where the obstacles are in before. So they can only use LiDAR to detect where they are. So looking at this setting, the first thing I would ask is, do we want to take a centralized way or a decentralized way? To me, the answer is quite obvious that's decentralized, because whatever centralized way, it may work well for not like a 4 agent here, but if I'm looking at 4,000, it's not look like a task that can be easily addressed. And also each of these agents, although they are having different destinations, they have some similarity. If you just look at each of the agents, they kind of deal with similar scenarios. They are getting to somewhere they need to avoid bumping into each other and also the obstacles. And so can we can we find some sort of a decentralized approach to find the control for this type of system, at the same time guarantee that nothing bad will happen. By bad, I mean no collision, they will get to their destination. So what we are doing here is something called the graph control barrier function. If you have never heard about barrier function, it's okay. I will tell you what is a barrier function. Now, what is a graph? A multi-agent system is naturally just a graph with nodes and edges. That's like a very natural thought, but whatever multi-agent system. For the node here, actually we are looking at two types of node. One is the agents, so we call VA, to denote all the agents. And the other is, remember, there's obstacles. But the thing is, we may not want to model every obstacle as like one node, because this obstacle will be very different. They have different shapes, different sizes, they have different moving velocity, and they could have different, they could denote different type of obstacles. It could be adversarial, could be friendly obstacles, could be static. It's kind of a lot of features we have to introduce. So we're looking at something that can relatively uniformly look at all these obstacles. We are looking at the end hitting points of the LiDAR. So whatever that obstacle is to the LiDAR, it's reading where kind of a point is hitting the obstacle. And the edges are really relatively easy. The edges are defined between two nodes when they are within some sensing range. So that's why you see sometimes there is a line between the two agents. That's when there is an edge and they can talk to each other. And also for the obstacles, that's kind of close enough within some predefined R. When we say this, the robot can see the obstacle, at least can see that point in the point cloud. So with that, we are ready to define our graph control barrier function. A graph control barrier function will take in the two things. One is the edge feature, one is a node feature. So edge feature means what you can transmit to each other on the edge. A node feature is whatever you want to define as a node. At the very minimum, it could be it's an agent or it's a LiDAR point. Or you could also, in this feature, define like a long vector denoting if this is adversarial, if this is moving, if it's just a human being. So all those are the node features. Whatever that is, for a graph control barrier function, it's a function that takes in these two features for the graph, and it will output a scalar value. The important part is output a scalar value. The scalar value says the function value is positive whenever this agent is safe, and it's negative when it's not safe. So it's very easy, these two conditions. And now you can see why it's called a barrier function, because h equals 0 is a barrier. It creates a barrier, tell you should always stay positive and never get across that sublevel set of h equals 0. And now with that too, that's kind of just the barrier. We still don't know how to control the system so they stay within safe. With that, the third condition really plays a role here. So the third condition is a little bit long. If you're familiar with CPF, it's very standard. If you're not, let me try to explain it in a way that's easy to understand. What the third condition is saying is, you see the first item, h dot. Forget about the second term. H dot is positive. What do you mean? It means the time derivative of h is positive, which means h value will only increase, which means if you start positive, you will be always positive. So you will always be safe. That's as simple as that. Now, why we have the second term here, alpha? Alpha is a class K function. The class K function is a monotonically increasing function that will pass the origin. So what is the second term is saying here? If I only have the first term, h dot is positive or non-negative, then what I ended up having is I'm staying further and further away from my barrier, saying like this room is safe, outside is not, and the wall will be the barrier. And if we all kind of stay away from the barrier, this room is not going to fit all of us. Some of us has to be closer to the barrier. And for the robot may have to do something close to the barrier. If we are being too strict, then the robot is just getting further away from it. You're not able to accomplish your task probably. And it's too conservative. And the second term here basically saying, I only need this h dot condition to be positive hold at the barrier. And what it's really saying is, the more closer I am to the barrier, the more sharp I should turn within the limit I can do. So that's basically what he's saying.
What is E sub y?
I'm sorry?
What is H feature?
edge feature. Edge feature is anything that you want the agent to talk to each other about. It could be one agent telling the other agent, I'm here, this is my position, or it could be my velocity, but we leave it open here. It could be anything that the agent wants to tell each other, and including, but not limited to, position, velocity, their actions, what they have said in the past, where their actions are. So depending on the feature, you will be able to have different levels of, things that robot can do together.
Because I see like a nice decomposition per agent.
Mm-hmm.
So like, I would have expected the H to be agent dependent, be H sub I.
Because H is defined for all agents. H is a function that's supposed to be defined for the entire graph whenever you see your neighbors. So H is one function, but and I will very quickly tell you, we're using a decentralized implementation for it. But for now, H is defined for the entire multi-agent system. So there's no H subscript of I. Does that make sense?
Yeah, but I'm eager to see what you're doing.
Yeah, okay, sure. And this H conditions here is for each agent I. If you project it to that agent, then all these conditions hold. But H itself is defined for the entire multi-agent system. And we can establish a theorem saying the existence of a graph barrier function guarantees the safety of the multi-agent system from, for example, non-colliding or safe initial conditions. If initially you're already unsafe, there's no way to prove your system is safe. So, and this safety is defined by whatever that set of as safe is include. It could be collision avoidance, could be battery, or anything you want to put into that safety set.
Bishop,
Yeah.
just a question. The V sub O, I'm assuming by LiDAR, you're actually meaning a time of flight sensor of a sort, where there's a single ray being projected at a given time. So you're only concerned with not extended objects, right? Just objects are treated as point objects?
No. So you will, this picture can probably tell you, but I will have more here. You can see multiple points can hit one obstacle. We're just not we're not recreating each obstacle, but only looking at what each endpoint of the LiDAR is hitting. So it's the obstacle you put in the environment can definitely be any shape. But like to us, it is like a point. Mm-hmm.
So your H dots on slide 13, is it the Lie derivative like standard CBF? So
Yes. It's Lie derivative. And I'll show the exact definition pretty much like next slide. So now while we have something defined as graph barrier control barrier function, it's pretty much ideal in a sense. It's like a single scalar function that can prove safety of my system, but we actually do not know how to find it. It's kind of like this. There are a lot of candidates you can choose. Usually, how would you find a function like this? You propose a template. That template comes with coefficients, and you want to find the right coefficients. So this function is actually, you have an explicit form of the barrier function. So finding barrier function, finding the Autonomy function, this has always been open research problems, and it's a hard problem. And I probably won't have time to go into why it's hard, but you can imagine for very large scale system, this function itself it's kind of unnecessarily have to be very complicated. Now, the way we are doing it, as its name suggests, we're using neural networks to represent this function. We not only represent the function, we represent both this barrier function, the graph control barrier function, and the controller as neural networks. And more importantly, we represent those as graph neural networks. Graph neural network has this nature of being able to be implemented in a decentralized manner. And it will be parameterized using what are the weights and biases of the graph neural networks. And we are going to find this function using the following loss term. I want to talk about this loss term to tell you this is actually a very intuitive way of constructing the loss term. And the same approach can be used to find other neural certificate functions, including contraction metric, the Autonomy function. So if you look at the papers, even from the broad community, usually this is a way of finding the neural certificate functions. You can see my loss term have 3 terms, and I have color coded it, so you can each color corresponds to one condition we want it to satisfy. And this condition is also super easy. If let's just look at the red one. So the red is the first condition. We want this H function to be positive when the state is safe for this agent. So what we do in the last term is to penalize it when it is not. So it's taking the maximum or the value of minus H and 0. Forget about that gamma for now, thinking about that as 0. Then it's just saying if it's positive, I don't have a loss. If it's negative, I have a positive loss. The more negative, the higher the loss is. Then if you do gradient approach, you should go to the direction of eliminating this loss. So that's how it works. And the three terms here are all kind of enforced in this way. Very intuitive way of doing it. And as with the question asked, the last one, the yellow one here is saying the last one, H dot, is a Lie derivative. And to do it, we have to do the chain rule of computing the Lie derivative. So that's as easy as it is, although it sounds like super easy. When in practice, you still need to do a little bit of fine-tuning of your neural network to find this graph neural network. And the architecture I've shown here, maybe I will not spend a lot of time talking about architecture, but this is a graph neural network that has a attention mechanism to handle the changing inputs. Like at any time, we will have different numbers of neighbors and different configurations of the points in the point cloud, but those will be going through attention layer to a fixed length input to find both the controller and the graph CBF. Now, if I look at what I actually found, remember the three conditions I want on my agent. It's a little bit difficult to show the third one, but remember it is positive when it's safe, it's negative when it's unsafe. So we can see each will have this contour show you, and each of this orange dot is an agent, and the black dot is an endpoint. So what we actually can learn in this case is very close to what we are thinking about. So when the agents are close, there is an edge, so you see a black connection. And when the closer it is, the more attention you want to pay to that agent. You can see that weight we have kind of marked for this agent here. The closer it is, either the other agent or the lighter the point is, then the more weight, or means it more attention you have to pay to this agent. And this is learned, like for each agent, we can have such a function overall. This can be kind of the similar copy can be put on as many agents as we want. Another really interesting thing we have observed here is in training, the best point of having this sort of configuration is we do not have to explicitly model obstacles in this setting. So we just need to randomly sample the endpoint of the point cloud. So basically each obstacle is just treated as like a point obstacle. But a big obstacle will be like the convex hull of some point obstacles. In this way, it can really generalize well to different type of settings. And I can quickly show you some of the generalizability result. There are different settings we have here on ground robots, flying robots, underwater robots. We have trained for the Dubin's car, for example. Dubin's car is a nonlinear car, but it's probably the easiest nonlinear car model you can use. We train on 16 of those and put the resulting controller on as many as agents as we want. On the left, you can see maybe 30-ish all the way to almost 1,000, or right about 1,000 on the right. Now, this setting here, we have the similar density in the sense you can see when we put more agents there, the space is also getting enlarged. From the animation, basically the cars get smaller and smaller. And we also find that this type of encoding can handle the changing density very well too. It's the same space if we have fewer agents here, and for the training, even if we dump more and more agents into the same environment, it's getting very crowded, it can still work pretty well. But you can imagine when I dump more and more agents, at some point, it will be so crowded that the agent cannot move around. So if we look at the more of the quantitative result, the red lines are our approach called the graph CBF. The middle one is a previous version of ours. It's not using the graph neural network setting, but the yellow one, the yellow lines are probably something you really are interested in is the PPO. It's a multi-agent PPO. It's the standard approach to do the multi-agent control. And we can see the different dynamics and different setting. We have a different setting, like we increase the density but have similar traveling duration, or we keep the density but either ask the agents to travel for similar duration or travel longer. You can see red is always outperforming the rest two, and especially the last setting. If we keep the density and keep the agents for traveling similar longer distance, the safety rate is almost perfect all the time. And I'm sorry, it's not safety rate, it's success rate. Success means it safely navigates to its destination on time. So it's not just getting there safely. You can always just be very conservative to be safe, to stay there. But what we're doing is asking the agent to reach their destination on time without bumping to any of the obstacles or to each other. And that success rate is almost the same even if you increase the number of agents but keep the similar setting. And of course, if we increase density, at some point the environment is so crowded they cannot move around. And if we ask them to travel longer, they will bump to each other more often along the way, so that in that case the success rate will drop. We so in the previous environments we didn't have obstacles. In this new setting, we still trained with just a few of the agents, but now put more agents as well as more obstacles. So there are all these random obstacles of different sizes, different traveling speed, moving around. During training, the car has no idea about where the obstacles are, but now you can see pretty much like on the right hand side, they're getting to their destination pretty well. And if we look at the success rate here by dumping more and more obstacles into it, the success rate is also almost perfect all the time. It's not going to decrease with the increasing number of obstacles. While if we look at MAPPO, it's kind of really doing a terrible job there in this like obstacle environment.
Okay, so can you characterize the failure once again?
Failure is the agent didn't get to their destination on time. It could be because they bump to if they bump to the obstacle, they will stop there, or they were being very conservative, just like stay there waiting for other agents to pass, then go. That's also a failure. So traveling to the destination on time without any collision is considered as a success case.
And in any of these scenarios, is there a possibility where the reachability is not even possible in the first place? You could have obstacles that make it impossible for anybody to travel to.
Yeah, that's a good question. So we are not setting like a deadlock. It's not like there is a area you get into, then the obstacle move here to completely lock you. In that case, it's definitely there's no way to get there. We are not setting scenarios like this. The obstacles we have tested is pretty much like the right hand side there. You can see it's some obstacles moving around, not intentionally forming a deadlock. Question?
So, I'm not very clear on how you actually eventually synthesize like controllers. So when you learn the GCBF, right? I'm talking about the low-level control aspect now. How do you now get control actions for the agent? So do you do like some type of optimization based on the barrier function you've learned? Is that how you get like you synthesize controllers for each agent?
So the controllers the controller and the barrier function are both neural networks, and they are both synthesized by that single loss function. You just sample that one loss function to do gradient, to do backpropagation, gradient-based backpropagation to get both. So that's how to get those. We're not introducing some particular optimization tool here to further improve it.
How do you ensure that H is always smooth? Like, how do you ensure the smoothness of H, like the GCBF? Since you need, I see that there's like an H dot, right? So it's possible that isn't it possible that the barrier function you learn is actually not, you can't compute, like it's not smooth. So what do you
So we can show that if that particular way of constructing the loss term, if it converges, it will give you a true barrier function. But of course, it's possible that it doesn't converge any machine learning algorithm. When you choose the wrong architecture, you choose the wrong hyperparameter, it could not converge. So we are kind of now assuming you can make it converge to a decent, amount. Like it's not exactly 0, but very close to 0. But I agree that to get it converge, there's some back and forth. You have to tune it to get it converge. But honestly, it's not that difficult. It's not like you have to do a ton of trials. It's pretty standard tuning methods to get it work.
So last question, sorry. So do you look at the graph as like because when you have several agents, then you have a very big graph, right?
Mm-hmm.
Very dense graph. So do you now kind of consider agents in cliques, or do you look at it as a fluid? Like, do you now consider the whole ensemble as a fluid, or do you consider agents in cliques?
So your question is about how we collect samples?
Yeah, something like that.
Yeah. The way we collect samples is kind of iterative. We let the agents to run around to give us the samples. And then we find a controller based on those samples. It may work well on those cases, but it may not work well on other cases. Then use this controller, we run out the agents to run around. It give us new set of samples, kind of like iteratively collect samples. Does that make sense? Okay. All right. So let me switch to the second topic. I may go a little bit faster there by skipping some of the technical details. But before I switch, I want to tell you that we are also building up the simulation environment that kind of more high fidelity and photorealistic. And this is a city, it's a virtual city, doesn't exist in the world. Because we wanted to, then the model for an actual city is too expensive. This virtual city is like 1,000 times cheaper than an actual city model. But it's a decent city. We can fly robots, we can drive boats, we can have the seaports where we have the automatic forklift to move things around the container. And there are thousands of such agents. This is a very nice environment that we are building up using the game engine to really visualize how well some of the experiments we're doing. So let me switch to the second topic because I think it's super interesting too. I may not have time to talk about all the details, but I know a lot of questions I got from the first line of work of neurocertificate is, what if I don't have the model? This is a very significant. I may have a good simulator, but I may not have a good model that is like a nice mathematical differential equation for me to use the neurocertificate. Particularly, I'm looking because I work in the aerospace department. We have a lot of airplane models that are built in Simulink. I don't know how many of you play with Simulink. It's not something that you can write down equation from a model. It's blocks connected with each other. For this case, like this kind of a summarization of decades of engineers' expertise. So they may find some particular lookup table work well. They put it here. There will be other physical components that they somehow code up. And the way you put them together is simulates each block, but link them using the semantics, the syntax and semantics in Simulink. Anyway, so we are interested in this type of problem, but we still want to make neurocertificate exist so we can say something about these type of agents. So we want to use reinforcement learning here. It's a powerful tool. It has solved a lot of interesting, challenging problems. But how can we find a neurocertificate in this case? So this is a work we recently presented at the Robotics Science and Systems Conference. It's a pretty good theoretical robotics conference if you're interested in that type of work. Versus ICRA is slightly more broad and more application. So we're looking at this problem and just formalizing this problem as something called a stabilize avoid problem. And it's very easy. We want to get the system stabilized while avoiding all the unsafe behaviors. From a controls perspective, a stabilize avoid problem is considered as a constrained optimal control problem, where we optimize some objective while making sure the system stays always safe. Well, safety is defined as this similar way. I have the function h. For now, this is not a barrier function h. H is just a definition of safe and unsafe. And you can probably tell it can be used as a barrier function. But if we're looking at this problem, and this is, by the way, also a standard problem in constrained reinforcement learning. People model this as if you put MDP underline it, then it's a constrained reinforcement learning. You can run any of the constrained reinforcement learning packages on it. Now, if I look at this problem, how could I find a Lyapunov function and a barrier function to still have the guarantees? It turns out it's not that difficult. By construction, you can get those. So if my objective have certain property, it's very easy. The property says for each state x k, if my loss term is 0 at goal and positive everywhere, which also makes sense, right? My loss, I want the agent to get to the destination, so it has a positive loss when it's not at the goal. Then we can show that the policy value function itself is a Lyapunov function. And this is a standard approach people can take. And here, you may already sense that this h, where the way we're defining safety, is also almost like a barrier function. And actually, if we take the inf of this h over all the states, it is a barrier function. It is a control barrier function. And we have to somehow massage this two certificate in the value function to have a value function that can at the same time serve as the Lyapunov and barrier function. Another good thing about this barrier function is it is an infinite horizon barrier function. So it can guarantee safety for as long as you want because the problem is defined so. Now we already know we can construct the value function to have the neural certificate. The problem is how we solve this problem. A standard approach is called Lagrangian duality. And I will tell you why it doesn't work. If it does, then all this stabilize avoid problem is pretty much solved, but it's not. Like people are still struggling with satisfying the constraints in those reinforcement learning. And I will tell you why it doesn't work. The approach we're taking is called epigraph form. And I don't know how many of you have heard about epigraph form. It's a standard thing in optimization, but we're adopting it to reinforcement learning. Let me very quickly talk about what is epigraph form. So epigraph form, if I look at a standard optimization problem, minimize some objective to satisfy a certain constraint. A textbook on optimization will tell you this is equivalent to the following epigraph form of minimizing an auxiliary value z such that these two constraints are satisfied. It's very standard saying, I want to minimize the upper bound of my objective function. Now, we further show that this thing in the middle is equivalent to a two-stage optimization problem. This two-stage in the inner loop, it is an unconstrained optimization problem, which is ideal. And but basically want to turn every constrained optimization into unconstrained, but the problem is how we guarantee that constraint is still satisfied. So we turn this into two-stage. In the inner loop, there is an unconstrained optimization, and outer loop, it's we have z here. You can think of z as a cost budget for satisfying the constraint, but you still want to optimize my objective. So the outer loop z here is only a scalar value. So that's outer loop. Although it has constraints, it is a scalar function that we can use a lot. You know, scalar value are always easier to optimize. You can just plot it and see where is the best place. Now, I want to be fast here. Just want to show then stabilize, avoid, constraint optimal control problem itself can use a similar approach of epigraph form to become a epigraph form of it. I want to show you this where this slide I think is more important why we want to use epigraph form in solving this type of problem, and basically why Lagrangian duality doesn't work. The fundamental reason is the gradient for the Lagrangian duality-based approach will blow up. It scales linearly with lambda. Lambda is a Lagrangian term we use. So maybe use a plot is easier. You can see that if I change my lambda value, you can see how the objective function is sensitive. And on the right-hand side is a green curve. That's the gradient. The gradient is linear. Then basically, if my lambda is kind of moving, if I slightly change my lambda, and that lambda will change in the optimization process in the unsafe region, then my whole objective will shoot up. And that's kind of making the whole optimization process not stable. While the epigraph form, the nice thing is this gradient is a constant. It's not going to scale with z. It remains a constant. So no matter how much I change z, my objective value pretty much stay on the optimal one. That's the reason. And now why this matters, because in constraint reinforcement learning, we cannot just, you don't even know where the safety, like how to keep my system safe. That's the question we are solving. Now it says If you're not keeping your system safe, then everything will blow up. Then that's kind of how it's a deadlock there. The Lagrangian duality is not working. So if we use epigraph form, so the way to solve it is very easy. We change this into a two-stage optimization problem. In the inner loop, we are facing you can see the inner problem is unconstrained optimization. We can use any reinforcement learning approach. We are using the policy, the PPO approach here. Now, for each sampled z, we have such a value function. Remember, our value function we have constructed to ask it to serve as a barrier function and a Lyapunov function. Now, in the outer loop, we have like a sampled value of z for each initial point. We can do like a regression. Here, we are using a neural network to approximate that one. It's a scalar function and optimize on that. The ultimate policy is going to be our policy at optimal z value. So that's how it works. If I run it, we have run it on a bunch of different examples. If I look at a standard kind of Majorco type of environment, it's a hopper. Now we are asking the hopper to jump to the green rectangle and stay there. You can see a difference there. Like there'll be a bunch of those, but our approach is kind of making a much better job. But what it makes more interesting is coming back to the fixed wing. This is mimicking the Top Gun. If you ever watch the movie, we're asking the airplane to stay within some narrow corridor and stay low because the detectors are up there, be detected and shoot if you're flying too high. So this is a stabilize avoid problem. We want to stabilize the airplane to be a low altitude and avoid collisions. Then here we are comparing between Lagrangian duality and our approach. We make it even more interesting. I can tell you a little bit more about this model. It's a typical Simulink model developed by the Air Force Research Lab, and it's considered as a high fidelity model for the F-16. We further enhance it because this is a GPS denied environment. You cannot have state information. We enhance it with a LiDAR, ask a LiDAR to be the eye of the airplane, not Maverick, because there won't be Maverick there. And we are trying to create like an autopilot Maverick that works much better. And now this is possible. And you can, this would be the ultimate environment we're creating, kind of having the mountains and the green lines are the LiDAR. And this airplane will have to keep a low altitude while traveling through this very narrow canyon environment. And the airplane has no clue about how the canyon is looking like, but it has to keep moving forward. What I'm happy to tell you about is this algorithm has much higher success rates than Maverick. At least the movie says it's a very difficult problem. Now, to end the talk, I want to tell you just one last thing. It's a work we just submitted to this next year's aircraft. We were motivated about we've been learning policy, proving this learned policy is safe. There's a bigger problem of maybe people still want to use their own policy, but want you to make sure their policy is safe or correct it when it is not. We have shown that this value function way of finding a neural barrier function can actually do more. It can help you correct your behavior even if you want to stick to your original policy. You can use any algorithm or anything you like to find a control policy. But online, we will use this safety certificate as a filter to do the following things. The way filter works is, without a filter, you can see that within the safety set is safe, outside it is unsafe. But with a filter, we ask you to use any policy you like. If it's safe, it will keep what you're doing. If it's not, it will do a minimum perturbation to correct you back to be safe. Now, the one we are showing here is still F-16, but I can show you like a more concrete example. This is when the airplane already traveled through the canyon, now want to do ground collision avoidance when there is a mountain in front. So when the safety filter is off, because in the training environment, it was trained to travel through a canyon, it was not trained to do ground collision avoidance. You can see how this last piece of mission is failed. But the same barrier function, we actually never used it. We use it to prove the system is safe, but we never use it for anything. We only use the policy. Now you can bring back that trained barrier function to have this filter on, and you can see like how well it's kind of helping with complete different type of missions. And we can also theoretically prove this approach gives you the largest safety region that you can get under some assumptions, of course, on the assumption that things converge, your learning process converge, and everything. And this compared to other type of methods like high-order CPF. It doesn't matter if you have never heard about it. It's like a classical way of doing it. And also MPC, you can see how bigger, this is just protected to 2-dimension, but how bigger that safety region is. And remember, this was never, the nominal was never trained for handling that. Sorry, the filter was never trained to handle this. The nominal was having some issue here. Let me just jump to my summary. So I hope that at least there are a couple of takeaway messages that was clear. We have talked about neural certificates, especially in the case of handling large-scale multi-agent system. We can use graph neural network to find a graph control barrier function for a fully decentralized, scalable, and generalizable collision avoidance control. The epigraph form we have developed further help you find the neural certificate in the reinforcement learning in a completely model-free setting, while the neural certificate we find can also be used as safety filters for any policy that you like. And many more applications using neural certificate, I'll be happy to give you a list if you're interested in those. There are still open challenges. Something I didn't make it very explicit just now, but you may already wonder, everything is learned. What can I say about this learned thing? So this is still an open challenge. We need to, the neural certificate we have learned can only be called a candidate certificate function. It's not a real one that, like the one you find a Lyapunov function using sum of squares, for example. We still need to verify this certificate is a valid one. But we believe this already help make the verification problem easier because you are now verifying a dynamical system that is high dimension and kind of moving on. This is a static function of scalar. So for simple cases, we can still use some neural network verification tools. But for the cases I have talked about, we're still looking for good approaches to verify this neural certificate. And there are basically 3 papers I kind of talked about in today's talk. I have the QR code if you are interested in knowing more. I have my lab website and also the GitHub page that contains everything that you have seen today. Okay, thank you.
Awesome. So that was a great talk. I'm sure we're going to receive a lot of positive feedback. Okay, 0 for 2 for my jokes. All right, we have like 3 or 4 minutes for questions. I know some people are asking questions midway through, but any questions before we let everyone go? Yeah.
Yeah, so very great talk, Professor Fan. So I'm kind of curious about the last bits you presented about the epigraph technique, right? So would it be right to say that the safe set in that scenario is actually forward invariant, that it allows you to deviate from
this one?
Yeah, it allows you to deviate a little from the safe set, but eventually, because the filter is on, you'll be driven, the control will drive the agent back to...
Yeah, so what it says here is within blue, you can safely explore within blue. Our safety filter will always keep you safe within blue, versus look at the forward invariant set of other approaches. They're relatively small. And this is only projecting to a 2D from a 17-dimensional system. You can imagine the whole total volume is really improved a lot.
Any other questions? All right, let's thank our speaker.